Okay, so let's do some practice. The best way to get comfortable with this material is just to dive in and start using it, and then um, you'll start to see how it becomes useful. Let's start with uh, arsenic. So As. So see if you can find arsenic on your periodic table. So now is when you always want to have a periodic table handy. Okay, so find your periodic table, have it at the ready. It's going to be your best friend for these exercises. All right, so if we find arsenic on our periodic table, you will see it's right there. Okay, so zoom in on number 33. Okay, As. Okay, so starting off with arsenic, a delightful element um, that serves as well as a poison. Okay, so definitely want to limit your exposure to arsenic, but let's take a look and see if we can figure out where the electrons in arsenic are located. Okay, so what we're going to do is use our periodic table to help us figure out what orbitals our electrons are occupying. Okay, so remember we have our S block over here, our P block here, our D block here, and the green is our F block. Okay, so we're just going to start from the beginning. Okay, we start with electron 1, electron 2, and then we'll just keep going through each one. And then we'll place those electrons in the corresponding orbitals. Okay, until we get to arsenic. All right, so for arsenic, we have 1s, 2 that we're filling. Okay, so we'll have electrons in there. Okay, so that gets us to helium. We need to keep going. Okay, so our next orbital we're going to fill here, we're back in our S block for n equals 2. One thing that I like to do is to just number my rows, and that reminds me what my energy levels are. Okay, all right, so we're into the 2 S's. Okay, so we'll put 2 electrons in there. That gets us to beryllium. Okay, so now we've covered those two. Let's keep going. So we can kind of go through this a little bit more quickly now. Hopefully we're getting the pattern. Okay, so we want to represent all of these electrons. These are filling in our P block, our 2, we're in the second row, so we're filling the 2p orbitals now. And we have 1, 2, 3, 4, 5, 6 spots, 6 electrons that get filled. So here's our 3 2p orbitals. So we're going to fill 1, 2, 3, 4, 5, 6. So remember your Hund's rule, okay? You fill unpaired electrons before you start pairing them up, okay? It's like we call that our sort of bus seat rule, okay? So remember, you always want to kind of have your own bus seat before you start sitting with another person. Usually electrons are the same way. All right, so now we've gotten to neon, essentially. So we got to keep going to get to arsenic. So now we're at 3, n equals 3, and we're filling the s orbital, the 3s orbital. So we've got 2 electrons going in there. And we'll keep going across the 3. Now we hit our 3p. Okay, we've got 1, 2, 3, 4, 5, 6 electrons again going into those p orbitals. 4, 5, 6. Okay, so that gets us to we're at argon now. Okay, we got to keep going, not there yet. So we've got some 4s electrons to start filling now. Oh, look at that, our 4s is next up. See how, hopefully you're seeing how the order of this orbital energy diagram is matching up exactly with just kind of moving across your periodic table with this SP, D, and F block labeling that we're using. Okay, so it should be matching up really well. Okay, so we just filled in our 4s electrons. Now we're hitting these red ones. Remember, these are our D block. Okay, my red laser pointer is not showing up there. So here's our D block. Okay, so now we are filling, remember you go down to N minus 1 when you hit the D block. Okay, and then before we forget, the F block is going to be N minus 2. So the number out front is not going to be 4, even though it's in that fourth row. Okay, when you hit these red ones, when you hit that D block, you go to N minus 1. So we drop down to 3D. Okay, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, which makes sense because we have 5D orbitals that can each get 2 electrons, so that works perfectly. So we'll put our 10 D electrons in there. Again, don't double them up until you've half filled all of them. Okay. All right, so now we're at zinc. Okay. Oh, we're so close. Okay, so now we've got 1, 2, 3 p orbital electrons to get to arsenic. Okay, so now we're back up. Remember, when you go back to the p's, you go back up to the same n value. So now we're at 4p. Okay, so we should hopefully, when we go to our energy level diagram, be filling 4p orbitals. And, oh, yes, perfect, matching up. So we have 3 electrons, we said, to get to arsenic. So we're going to go 1, 2, and 3. So remember, 1 electron in each orbital before you start doubling up. Okay, so we have, I think, successfully filled out our orbital diagram for arsenic. Okay, so again, this just shows you where all of your electrons, okay, where all of your 33 electrons are located in arsenic. Okay, now we'll start to see that the fact that this has some unpaired electrons in this higher energy orbital, okay, that's going to be important for us later on, okay, when we start talking about reactivity and the types of ions that arsenic likes to make, okay, but for now we're just getting comfortable putting electrons in these different orbitals. Right, so hopefully you can see how we can just follow our periodic table, just move left to right, top to bottom, going across, and that tells us what orbitals we're filling. Okay, and it matched up real nicely with the order of our orbitals on this chart. Okay, so let's do one more exercise here. Let's put together the electron configuration for arsenic based on what we've just done here. Okay, so remember, our electron configuration has basically just tells us where the electrons are in our atom. Okay, so we're going to start from the beginning. Okay, start from your first orbital, your lowest energy orbital. So we get 1s2. There's 2 electrons in that 1s orbital. Our next orbital is the 2s, so that's going to come next. So you go low energy to high again, always. So we have 2 electrons we see in that orbital, so we'll say 2s2. Next one is 2p. Okay, we have 6 electrons that we put in that 2p orbital. So we'll say 2p6. And then 3s, another 2 electrons in that 3s orbital. Next orbital is our 3p. We see that there are 6 electrons in there. Okay, so now we're up to 4s. Okay, so we'll say 4s. We got another 2 electrons in there. Next up is our 3D, and we have 10 electrons in there, right? So we got 5 orbitals with 2 electrons each, and then that leaves us with our last orbital. So we have our 4p, and we have 3 electrons in there. Okay, so this is the full electron configuration for arsenic. Okay, so again, you see exactly how many electrons are in each orbital. Okay, what orbitals are getting filled here. Okay, and we can see that we have 1 unfilled. This orbital on the outside here, that one's not completely filled. And that's going to tell us later on that arsenic has a little bit of room to react with us. Okay, so if you get things, if you end up with orbitals that are totally filled up like this one, okay, that means that they tend to be less reactive. Okay, so I'll let you kind of hazard a guess as to what all of your noble gas electron configurations look like, right? Okay, so this is a full electron configuration for arsenic. One thing that you'll notice is if you look up electron configurations, like on Wikipedia or in a table somewhere, a lot of times you'll see them group all of the N's together, so all the threes would be together, so it might not be in quite the order that we've written here when you look it up. I don't really care what order you put it in, but I just tend to go in the order that my periodic table tells me to fill. And so, again, sometimes you'll see all the threes grouped together, all the fours grouped together. Okay, but as long as you've accounted for all of them, that's the most important part. Okay, so you might be saying to yourself, well, okay, good, I get this, I can write an electron configuration, but this is going to get really tiring to write out all the time, especially when we get down to some of these elements with all of these electrons in them and all of these orbitals that we're filling. And you're right, and chemists are lazy, so we come up with a shortcut to write electron configurations. Okay, so what we can do here to shortcut arsenic is to find the noble metal that immediately precedes the element that you're interested in. Okay, so for arsenic here, the noble gas that immediately precedes it is argon. Okay, so what we will do is write what we call a noble gas core abbreviation electron configuration. Okay, so that's going to look like you put it in brackets, you put your noble gas that comes immediately before in brackets, and what that says is this is just represents all of the electrons that go up to argon. Okay, and now I just have to worry about the ones that come after that. We call those ones in that bracket, we'll say those are the core electrons. Okay. Okay, so that essentially takes care of up to here, right? So that would be the electron configuration for argon, right? So now we just have to write what's left over after that. So once we get to argon, oops, to point. Once we get to argon, we're filling our 4s2, 3d10, 4p3. Okay, so those will come after. So we have our 4s2, 3d10, oops, 4p3. All right, so this is our noble gas abbreviation. Either option is acceptable, and you'll see probably more commonly this option when you're looking at references, just because it saves a little time in writing out. It's a little bit easier to work with. Okay, let's do another example. So I want you to see if you can do a similar process for the sodium ion. Okay, so we want Na plus. All right, so what does the positive charge mean? That means that we've lost an electron. Okay, so we're missing one electron. Okay, that gives us a positive charge, because remember, electrons are negatively charged. So if our ion is positively charged, that means that we've lost an electron. Okay, so do the same process and see if you can account for that missing electron. Okay, what that's going to look like. So maybe start with sodium and then take away an electron would be my approach. So pause the video, take a minute, see if you can fill in your orbital diagrams here with your electrons. Again, use the trick of just going across our periodic table. Okay, this one shouldn't be too bad, a little bit better than arsenic. Okay, so here we're looking at your sodium. Okay, so again, take a minute, see how you do. Fill in your orbital diagram and write out a electron configuration for sodium. So do a full one and a noble gas abbreviation for good measure, and check back here and see how you did. Okay, so checking back here. Hopefully you've taken a stab at filling in your electron orbital diagrams, writing your electron configurations. So what I've done here is to fill in the electrons for neutral sodium. Okay, so here I've put 11 electrons in my orbitals as I go across, so filling the 1s, the 2s, the 2p, and then we've got 1 electron in the 3s for our neutral sodium. Okay, so remember we want the sodium ion, so what we want to do is take away 1 electron from our neutral situation. Okay, so if we remove an electron, I'm going to take out the last one that I put in, which was the one in that 3s. And then what are we left with? Okay, we're left with 10 electrons, okay, and they completely fill these subshells, okay? And it turns out, if you look at your periodic table, we now match up with our noble gas neon with 10 electrons, okay? So because of that, because sodium plus has the same number of electrons as neon, we say that Na plus is isoelectronic with neon. Okay, so iso means same, okay, and electronic, so same number of electrons as neon. Now, this is really important to be able to recognize when something is isoelectronic with a noble gas, okay, because that gives you some information about what types of ions that element tends to like to form. Okay, so if you know anything about noble gases, you probably know that they are, so this row here, right, is our noble gases, so helium, neon, argon, krypton, okay? Those gases are really unreactive. They're not totally unreactive. We can do some bonding with them, okay, under really special circumstances, but for the most part, we say they're inert or unreactive, okay? So that's a really stable, we say that that's a really stable electron configuration, okay? And that stability comes from the fact that, as you can see here, all of the subshells are totally full for that given energy level. So here we've gone up to n equals 2. Every orbital, okay, that we could fill is full of electrons, okay? This situation, if we look here, this element, this atom, this ion, okay, whatever you're looking at with a totally full set of subshells, doesn't want any more electrons. It's really happy the way that it is. Okay, it also doesn't want to lose any electrons. Sometimes it's easier to lose an electron to get to this situation, sort of like our sodium plus, right? So sodium really is not super excited to hang on to that last electron that we put in. It's happy to give it away because that means that it can get to a stable full subshell configuration. Okay. So you'll start to see, again, that's one of the utilities of drawing these kinds of diagrams, is that you start to see visually, okay, how happy is my atom or my ion? Okay, how much does it maybe want to lose an electron, or maybe it wants to gain an electron? And that's going to tell you a lot about the kind of reactivity that it likes to engage in. Okay, so this really explains why sodium actually likes to take on +1 charges, and all of your alkali metals, all of those first column metals are going to have a similar electron configuration. So you'll just start having 1 electron up here in these higher energy levels as you go down the periodic table. Okay, they're all going to be pretty happy to get rid of that 1 electron. Okay, they're all going to want to take on essentially that +1 charge. Okay, so last but not least, here are your electron configuration options for Na+. Okay, we already said Na+ is isoelectronic with neon, so you can just write your noble gas core. It's going to be neon. If you want to write out the electron configuration fully, we have 1s2, 2s2, 2p6, which again matches up with the full electron configuration for neon. All right, our next example is going to be actually one of our exceptions for filling our orbital subshells. Okay, so there's a couple of exceptions that we want to be aware of. They're rare, but they're ones that you want to know about. The first one is going to be chromium. Okay, so chromium is one of our transition metals. Okay, so let's find chromium on our periodic table. So it's right here in our D block, transition metal block. Okay, so your task right now is going to be to predict how you would put electrons, how you would put the 24 electrons for chromium into your orbital subshells. Okay, so go ahead and fill those up how you would do it based on our previous examples. Okay, and then we'll come back and take a look at any kind of modifications we might want to make for chromium. Okay, so take a minute to fill those in and then come back to your video. Okay, so this may be what you ended up with. Okay, if you filled in your electrons as we did in our previous examples. Okay, so again, just going along, filling our periodic table as we go in order left to right. Okay, so we fill up all of these, we get to 4s2, and then 3d, 1, 2, 3, 4 electrons in our 3d orbitals. Okay, great. All of our electrons are accounted for. They're going in order from low energy to high energy. Everything's good. Okay, one thing that I'm going to remind you of is, remember how we said before that totally full subshells are really ideal and kind of our stable situation? Okay, well, if your atom has a chance to get to a totally full or even a totally half-filled subshell, okay, without expending a lot of energy, it's going to do that. Okay, so what chromium actually prefers to do, rather than staying in this configuration, okay, is it prefers to, what we say, promote one of those 4s electrons over into the 3d orbitals. Okay, so what you end up with is 1 electron in your 4s orbital and 5 electrons in your 3d. Okay, your electron configuration for chromium, if you were to look that up in like I said, in any kind of resource, what you're going to probably see is something that looks like, let's use our noble abbreviation. So the noble gas before chromium is argon, and then we get 4s, what you'll see is 4s1, 3d5, not argon 4s2, 3d4. Okay, so this is probably what you might have predicted, again, based on our original rules. Okay, but because chromium has a situation where if it pops that 1 electron from the s orbital up into this d orbital, then it gets a set of half-filled subshells, which is simply just more desirable for the atom. Okay, it's just energetically a better situation. It makes it happier. Okay, so you'll see that happen for chromium. All right, and you'll also see it happen for copper. Okay, we'll do copper as our next example. Okay, next example, another exception to our rules for filling our orbitals is going to be, as promised, copper. Okay, so here we're now at 29 electrons. Okay, we want to do copper. So based on our conversation that we just had for chromium, why don't you see if you can predict how copper might like to rearrange its electrons a little bit to get a little bit of a happier electron configuration than we might predict with our basic rules of orbital filling. So take a minute fill in your orbitals and see where you think copper is going to want to end up. Okay, so hopefully you took a stab at filling in the electrons for copper, and what copper ends up wanting to do is you might have initially ended up with 4s2 3d9, okay, so one little lonely electron over here, okay. So what copper likes to do is to promote that 1s electron over into its 3d orbital here, so we end up with a fully filled 3d subshell and a half-filled 4s subshell. Again, just energetically more favored than kind of having that slightly underfilled D subshell. Okay, so electron configuration for copper, when you look that up, you have again our argon noble gas core, and we have 4s1 3d10 is probably going to be the configuration that you see when you look this up, and not, if you're not paying attention, you might go on autopilot and do the 4s2 3d9. Okay, so copper, again, one of our exceptions, likes to promote that s electron up into the d orbitals to get that nice full subshell, nice stable rearrangement. Okay, a couple of last practice just to make sure you feel comfortable with your electron configurations. So why don't you see if you can draw the electron configuration, or write the electron configuration for magnesium. Okay, so magnesium over here in our alkaline earth metal column. Okay, so hopefully you ended up with one of these options for the magnesium electron configuration. Here's your full version. Here's your noble gas core version. Okay, so next question for you would be, what would you expect the electron configuration to be for a magnesium ion? So ask yourself, if the goal of most atoms is to get to a noble gas kind of electron configuration, what kind of ion do you think magnesium is going to want to form? Okay, hopefully you're thinking to yourself, well, it's real easy for magnesium to get to a noble gas core if we just get rid of these two s electrons, these two outer s electrons. And that's exactly what magnesium likes to do. Okay, so magnesium is going to want to make ions that have 2+ charges. Okay, so here it's going to lose those two 3s electrons. Okay, and that's going to get it to a noble gas core. Okay, hopefully this video has helped you to feel more comfortable with electron configurations and our orbital diagrams. We're going to use these tools a lot moving forward, as promised, to help us to make some predictions about the reactivity of different atoms and why they tend to form the molecules they like to form. So this is going to be some really powerful tools that we're going to have under our belt. So again, keep practicing, and thanks.